let's go ahead and get started, so we can go on and do other things tonight. So before I get started, any questions? Anything in general? This is your hour. Okay. So tonight we're gonna review sections 3A and 3B, and then Thursday night we'll review sections 3C and 3D. So, beginning with our discussion of the second law and the introduction of entropy. So the second law, we looked at a lot of different statements, verbal statements of the second law, and you have to be comfortable with your way of explaining the second law in your own words. So the book suggests a couple of them. No process is possible in which the sole result is the absorption of heat from a reservoir and its complete conversion into work. So you have a hot source and taking heat from the hot source and converting it into work. It's impossible to do that with 100% efficiency. It's impossible to do a complete conversion of that heat taken from the heat reservoir and convert it into work. And the other idea that's maybe even more important to this discussion is that heat does not flow spontaneously from a cold body to a hot body, to a colder body to a hotter body. And so that introduces the idea of spontaneity, and that's really the most important concept that we have to keep in mind when we're talking about the second law in our introduction of the concept of entropy. We introduce entropy because after our discussion of the first law, there was nothing in the first law that would tell us whether or not a process would take place spontaneously. And so that's kind of what we were searching for in introducing the second law, thermodynamics. And it leads to the introduction of entropy, is that state function or that quantity that we can trust to tell us whether or not a process will take place spontaneously or not. So that second statement that we read, that heat does not spontaneously flow from a cold body to a hot body, that captures this idea of we're looking for something that will tell us whether or not a process will take place spontaneously. And that quantity is entropy, that state function is entropy. So that leads to our various definitions of entropy. We have the thermodynamic definition of entropy. So we've seen these a number of times at this point, but our thermodynamic definition of entropy is that change in entropy will be equal to or greater than dq reversible over temperature. So, or actually we're defining that as an equality at this point. It's equal to. So that's our thermodynamic definition of entropy. And so we need to know that, but we also need to understand why it's defined in terms of the amount of heat transferred for a reversible process. Because not all of our processes that take place in the system will take place reversibly, but we use the amount of heat transferred that would be transferred by a reversible process in our definition of entropy. So we need to remember why our definition is based on that and be able to explain it. We've talked about it before in class. And so if we're introducing a new state function, which is going to capture this idea of spontaneity, we want it to be a state function because we want the value of the change in entropy for a process to not depend on the path or how the process takes place. And so we're looking for a quantity that can be defined as a state function. We see that we relate the change in entropy to the amount of heat transferred, and that gets back to this kind of schematic drawing in your book, which says that an increase in entropy is associated with an increase of the dispersal of energy. And so we distinguish how the effect that work has on a system. It's an orderly displacement of molecules. But when we transfer heat to the system, then it causes an increase in the dispersal of the molecules. So that's associated with a dispersal of that energy. So we're defining our new state function in terms of the amount of heat transferred during the process. But we know that heat generally is a path function. It usually depends on how the process takes place. But if we divide the amount of heat transferred by the temperature at which the process is taking place, it turns out that leads to a quantity that the change for the process is independent of how the process takes place. That satisfies one of our requirements for defining a state function. We're taking a path function, but when we divide this path function by temperature, then it turns out that the overall change for a process is independent of path if we define entropy in that way. The other thing that's important is we define, as I mentioned before, that we use dq reversible in our definition. And why is that important? And that is important because if we don't, well, there are two aspects to that that are important. One is that by defining a specific path, then we've taken away the path dependence in a sense. We've defined only a single path, and it's the reversible path. So if we didn't define the reversible path, then our answer would depend on how the path. I mean, if we did the heat transferred in a free expansion of a gas, that would be different than expansion against a constant external pressure, and that would be different than the heat transferred for a reversible expansion. So if we didn't specify a path, then our definition of entropy, the amount of entropy changing going from some initial volume to some final volume would depend on how the expansion takes place. But by defining it as the amount of heat transferred for a reversible expansion, then that restricts the path to one answer. So that takes away the path dependence. The other thing that is important about it being reversible is that it indicates the maximum heat transferred. So if we chose the amount of heat transferred for expansion against a free expansion, it would be the minimum heat transferred. It would be zero. Change in entropy would be equal to zero if it was for a free expansion. But by defining the amount of heat transferred for a reversible process, that ensures that not only will that path be restricted to one path, the reversible expansion, but it will also ensure that it has the maximum heat transfer that's possible for that process, which is defined by the reversible expansion. So you kind of need to be able to appreciate all of these aspects to why entropy is defined in that particular way and why it depends on Q reversible and not just Q. The other thing to keep in mind is that ds, I have no subscript here. That implies, or that indicates that we're talking about the change in entropy of the system. We distinguish that from the change in entropy of the surroundings because if we're talking about the surroundings, then we put a subscript here that indicates that we're talking about the surroundings. But if you see no subscript in your question, or then we're talking explicitly about the change in entropy of the system. And so this brings us to this point. How do we define the change in entropy of the surroundings? Well, change in entropy of the surroundings is defined as dq surroundings divided by T. So there are two things that are important about this definition. One is that you'll notice that I didn't explicitly write down dq reversible. And that means because if we're thinking about, let's say that this is our system, and we have a transfer of heat from the system to the surroundings, surroundings is the rest of the universe, then it doesn't matter what size Q is. The impact on the surroundings is going to be an infinitesimally small impact on the surroundings, and therefore that satisfies our definition for a reversible process taking place, because Q, first of all, Q surroundings is equal to minus Q cis. So if we're going to calculate the change in the entropy of the surroundings, the change in heat to the surroundings is going to be minus the change in the heat of the system, because the system's giving up that amount of heat to the surroundings. We know that our definition of change in entropy for the system is defined with Q reversible, but in our definition of ds for the surroundings, it's dependent on just Q surroundings, I'm not explicitly saying Q surroundings reversible, because any transfer of heat from the system to the surroundings, because the surroundings is such a big heat sink, it's the rest of the universe, that any transfer of heat from the system to the surroundings has an infinitesimal impact on the heat content of the surroundings, because it's an infinitesimal transfer of heat that satisfies our definition of a reversible process. So that's important to recognize that, and to understand how to properly calculate the change in entropy of the surroundings. So, I think you've seen a question before: why is the entropy of the system defined in terms of Q reversible, but the entropy of the surroundings is defined in terms of minus Q system? Here it's Q reversible. So you need to be able to explain those, why the entropies depend differently on either Q reversible or minus Q cis. Everybody clear on that? Okay. So the other, we talked about two ways in which we define entropy. One is the thermodynamic definition of entropy, and then we have the statistical definition of entropy, in which S is equal to the Boltzmann constant times natural logarithm of W, where W can be thought of as the probability of a state existing, or the number of possible microstates that exist for that system. And so two very different ways in which we define entropy. This particular definition of entropy plays an important role for us in our discussion of the third law of thermodynamics, where we talk about third law entropies, and this ties to the concept of residual entropy, because we'll get to this in a few minutes, or in a little while, but the third law states that the entropy of a pure crystalline substance is equal to zero at T equal to 0, but a pure crystalline substance means that the lattice is perfect. And so if there's more than one way for the molecules to orient in the lattice, then it's not a perfect crystalline lattice. In other words, there's some disorder in the lattice, and that is reflected in the number of possible microstates that are available to that substance. And so in the case where the molecules orient in the lattice in more than one way, it's an imperfect lattice, and that gives rise to what we refer to as residual entropy. So that's where the statistical definition of entropy is going to play an important role in a little bit in our discussion. Okay. So we just went through the discussion saying that we decided that we needed to introduce a new state function that could capture this idea of indicating whether or not a process will take place spontaneously. That new state function is entropy, but now we want to prove that it's a state function. And so one of the ways that we prove it is a state function. And we said that there were three ways in which we do that. One is to prove for a special case. In our special case, our example is the Carnot cycle. And the second, prove that it is true for any substance. Any working substance. And three is to prove for a general cycle. And so what we did in class, or what we focused most on in class, is going through this proof for a special case for the Carnot cycle. And so we have our pressure versus volume plots. We have our, oops, it's really bad. We have our Boyle's law isotherms. Can't spell either. And then we have our adiabats. So we have 4 steps. We have our initial step, let's say A, going to our second state, B, our third state, C, and our fourth state, D. So we have 1, 2, 3, 4 steps. 2 of these are adiabats. And so what we need to prove in this case is that the change in entropy for the complete cycle is equal to 0. And if this is in fact true, for this complete cycle, we start and end at the same state. So for the complete cycle, if the way in which we've defined entropy satisfies that requirement, then the change in entropy should be equal to 0 for the complete cycle. So that must be equal to the sum of the changes in entropies for state 1 plus entropy change for step 2 plus the entropy change for step 3 plus the entropy change for step 4. In 2 of these cases, step 2 and step 4, these are adiabats. So step 2 and step 4 are adiabatic, which means that Q equal to 0, which means delta S is equal to 0. So 2 of these, we have this delta S 1 plus 0 plus delta S 3 plus 0. So delta S1 plus delta S3. If delta S for the complete cycle if our definition of entropy is supported for being a state function, then the sum of these 2 changes in entropy will be equal to 0. So now we have to consider the 2 steps, 1 and 3, for which we need to calculate the change in entropy. So for step 1, it's for an isothermal expansion. So we have our definition says we're going to use dq reversible over T. And these are reversible. These are all defined as reversible in the Carnot cycle. So we have dq reversible. And the other kind of nomenclature we use on this diagram is that this is an isotherm and this is an isotherm. We say that this is at the hot temperature and this is the cold temperature. this is QH over TH for this step number 1. And delta S3 will be then defined in the same way, will be equal to QC over TC. So in order for this to be true, that means that QH over TH plus QC over TC must be equal to 0. That means that QH over TH must be equal to minus QC over TC. This can be written as QH over QC must be equal to minus TH over TC. Now, I remember seeing this on the quizzes. A lot of you came to this point and you said, okay, because this must be true, that proves that entropy is a state function. But that doesn't prove it. That tells you what you need to prove in order to prove that entropy is a state function. If entropy is a state function, this relationship must add up to 0. In order for this relationship, these two terms to add up to 0, this must be true, which can be rearranged to this, and so this must be also true if entropy is a state function. But that itself doesn't prove that entropy is a state function. So you need to go through and prove that, in fact, if you add these two terms together, they add up to 0. Okay. So if we look at delta S1 is equal to QH over TH, well, this is isothermal reversible. So for isothermal, delta U is equal to 0, which is equal to Q plus W. Since delta U is equal to 0, this is our first law, since U is equal to 0, then QH is equal to minus W. This is isothermal reversible, so it's isothermal reversible, so W is equal to minus nRT, natural logarithm V final over V initial. But we're talking about step 1, so V initial is A, VA, and at state B, the volume is V sub B. So I can say this is equal to minus nRT, natural logarithm of VB over VA. For Q, then, therefore, Q for the H, the high temperature step, is equal to positive, it has the opposite sign, positive nRT, natural logarithm VB over VA. Okay, now for step number 3, my V final is going to be V sub D, my V initial is going to be V sub C. We're going in this direction. So here we go through an isothermal expansion, an adiabatic expansion, an isothermal compression, and adiabatic compression. So V final is V sub D, V initial is V sub C. So Q sub C is going to be equal to positive nRT, natural logarithm of V D over V C. So I need to show that this sum is equal to 0. I've now defined, well, and I should keep track of the subscripts here. So I have TH and I have T sub C. Okay. Now, I don't want to go into that board because I want to stay in view here. So erase this. So the change in entropy at the high step for step number 1 is equal to QH So this is where these ratios of the volumes become important. And how we get the ratios of the volumes and the relationship with the temperature is we have to take advantage of what we understand about how volume and temperatures are related for adiabatic expansions. And that rule is for an adiabatic expansion. We have to use the rule that V times T raised to the C is equal to a constant. That means that if we're looking at here, at this adiabatic step, then the volume times TH raised to the C will be equal to VC times TC to the C. So if I do that, for relating the volume and temperature of these 2 points, I'm going to have V sub V times TH to the C is going to be equal to V sub C times T to the C raised to the C. From this adiabat, I'm going to know that V sub A times TH to the C is going to be equal to V sub D times TC to the C. That's a part that's really important for making this proof. It is recognizing you have to make use of the relationship that allows you to relate the volume and temperature along an adiabat. So if I multiply these 2 relationships together, and I have to multiply them together in such a way that I get one cold temperature and one hot temperature together on each side. So I'm going to take this side times this side. Let's say I'll have VB times VD TH to the C TC to the C. This will be equal to VC TC. Oops. VA TC to the C TH to the C. Now I have a TH and a TC to the C over here, and I have a TH and a TC to the C over here, so I can cancel those out. I'm left with VB VC is equal to VC VA. And then the ratio I need over here is I need a VB over VA. So if I divide both sides by VA, I'm going to get a VB over VA is equal to, oops, what did I do here? VC. What did I do? It's VD over
VB times VD.
VB times, it's right here. VA and C. So VB and VC and A. Okay, so I have VB over VA is equal to VC over VD. When I go back to this relationship, then I'm going to use this result. I have VB over VA over here, and I have a VC over VD over here. So if I invert this, if I invert this ratio, I have to change the sign up front. I have NR natural logarithm VC over VD. But if I just showed that VC over VD is equal to VB over VA. So this is equivalent to minus NR natural logarithm of VB over VA. So this part is the same, but they have an opposite sign. So I've just shown that the change in entropy for step number 1 and step number 3 have equal magnitude but opposite sign. So when I add those 2 quantities together, I get a value of 0. So that's the complete proof for the Carnot cycle. You can't just draw this conclusion and say, okay, therefore that proves that entropy is a state function, because this must be true. Yes, it must be true, but you have to prove that that's true to prove that the change in entropy overall is equal to 0. So. Everybody good with that? Any questions? Yeah. All right. I'm going to erase that. So the next thing I want to spend some time on is going over the clauses and quality plays such an important role for us. So we talked about deriving. So we've learned how to derive clauses and quality. We've said show how it is consistent or supports our definition of entropy. And we also extend it to define conditions for spontaneity. And we also use it to then derive the Helmholtz and Gibbs energies. So we get a lot out of this clauses and quality, which isn't given much space in your book, but we actually use it for a lot in this class, or in thermodynamics. So if we review that, we start for the derivation. Start with one is recognizing that that the absolute value of the amount of work done for reversible work will always be greater than or equal than the amount of work done in an irreversible. And I'm going to talk with changes here. Let's forget that part. dW reversible is always greater than or equal to d work. So I'm putting absolute value signs here because the way, by convention, we define the change or the sign on W to be negative if the system's performing work. So if I take away, that means that this quantity is intrinsically negative if the system's performing work, and this quantity is intrinsically negative if the system's performing work. If I take away the absolute value signs and I still want this side to be greater than or equal to this side, then I have to take the negative of this negative quantity. So if I do minus dW reversible, be greater than or equal to minus dW. And I think that part's always maybe a little bit confusing to people. This is a negative quantity if the system's performing work. If I take the negative of that negative quantity, it's a positive quantity. So that positive quantity is going to be bigger than the size of this positive quantity. Okay. I can, if I subtract, or no, I'm going to add dW to both sides. Add dW to both sides. So I'm going to get, when I do that, I have dW minus dW reversible is greater than or equal to 0 when I do that step. And we ultimately, we want to get the relationship between heat transferred, not work performed. So we want relationship for heat transferred, because we're talking about entropy that's defined in the context of the amount of heat transferred, not W. So use first law equation. So we have delta U is equal to dQ plus dW, which, because internal energy is a state function, it's path independent, so I can also say that change in internal energy must also be equal to dQ reversible plus dW reversible. I've find this relationship up here. So that says that this quantity must be equal to this quantity. So if I want to substitute for this in terms of heat transfers, I have a dW minus dW reversible. So if I subtract dW reversible from both sides, I'm going to get dW minus dW reversible is going to be equal to, I've subtracted dW reversible from both sides to get this expression. Now I'm left with dQ reversible over here, and I'm going to subtract dQ from it over here. So dQ, using the first law and taking advantage of the fact that it's a state function, so this path must be equal to this path, I can group these terms on the left, which is what I want to substitute for. And I should be able to substitute this for this term. So therefore, I can say that dQ reversible minus dQ must be greater than or equal to 0. Now I can divide all terms by t. So I have dQ reversible over t minus dQ over t is greater than or equal to 0. I can use thermodynamic definition of entropy. ds is equal to dQ reversible over t. So I can substitute with this for this term with ds. So I have ds minus dQ over t is greater than or equal to 0. And now I can solve for ds. We have ds is greater than or equal to dQ over t. And that's Clausius inequality. Okay. So that's one of our goals, is to derive that expression. Now, the second point is show how that Clausius inequality is consistent with or supports our definition of entropy in the context of the second law. And we consider isolated system process. Consider a process in an isolated system. For isolated system, Q equal to 0. Therefore, ds must be greater than or equal to 0. That means that for a spontaneous process in an isolated system, the entropy cannot be less than 0. It can be greater than or equal to 0. And that means that for a spontaneous process, that the entropy must increase for a spontaneous process in an isolated system, and that's consistent with our mathematical statement of the second law. So that's another thing we said that we needed to know at the outset. One is the verbal statement of second law, but also the mathematical statement. Of second law. So we have that the delta S plus delta S of the surroundings, delta S of the total, or we say delta S of the universe, equal to delta S of the system plus delta S of the surrounding must be greater than or equal to 0. So we have a verbal statement of the second law, mathematical statement of the second law. Then we have our thermodef of entropy, and we have this showing why the Clausius inequality is consistent with or supports our definition of entropy in the context of the second law. It says that entropy must increase for any spontaneous process, which is consistent with our definition of entropy. Entropy is the state function we define that allows us to determine whether a process will take place spontaneously. And it also says that for that spontaneous process, that the change in entropy has to be greater than zero, which is consistent with our mathematical statement of the second law. Yeah. Okay. Everybody good with that? Yeah. Okay. So I'm going. Yep. I'm going to erase that so I can stay on one board. Yes.
The question about the Q, saying for a spontaneous process in an isolated system, the Q should be zero.
For an isolated system, Q will be zero. There can be no heat transfer in an isolated system because no heat or material can be
Also,
transferred.
the change.
So, right.
Okay.
Yeah. Okay. So, let's go ahead and erase this. So we're starting with our Clausius inequality. And we consider, one thing we did is we say, okay, how do we know that entropy is our quantity that's going to determine whether or not a process takes place spontaneously or not. So we consider, we often restrict the process to take place in a certain way. So we can do that. In this case, what happens if we restrict process to constant volume, let's say. So we know that if for constant volume, with our definition of the first law, we have dq, du is equal to dq plus dw for constant v dw equal to 0, because this is equal to pdv minus pdv. So dq at constant volume is equal to du. So for a constant, volume, we can rewrite that relationship as ds is greater than or equal to du over t. And we can multiply by t both sides, and we have tds is greater than or equal to du. And so when we restrict the process to take place at constant volume, we have our Clausius inequality, which is our guide, now has two quantities that can change, either entropy or internal energy. So that we consider, okay, one criteria is, let's say that if the internal energy is held constant, then ds must be greater than or equal to 0. So if the internal energy of the system doesn't change, in order for the process to take place spontaneously, there must be an overall increase in the entropy of the system. And so one can think of that as like what kind of an example can you think of that would satisfy that? no change in the internal energy, but for the process to take place, there must be an increase in the entropy. And you can think of a free expansion at constant T. It's an isothermal free expansion because T equal to constant, then U equal to constant. That's holding U constant. But the gas undergoes a free expansion. If we calculate the amount of heat transfer for the reversible expansion, which is how we define entropy, then that will lead to a positive, an increase in the entropy, and that's what that restriction tells us. So this, in this case, where we use the Clausius inequality, we hold the process to take place at constant volume, so we can change the internal energy. We can substitute internal energy for dq. For the process to take place spontaneously, there must be an increase in the entropy of the system. Alternatively, if we hold the entropy, if ds equal to 0, so constant entropy, then there must be if the entropy is constant, then du must be less than or equal to 0. So u must be less than or equal to 0 if ds is equal to 0. And why does that make sense? Well, if ds is equal to 0, in order for the system, for the process to take place spontaneously, delta S of the universe equals delta S plus delta S surroundings. If ds is equal to 0, well, this is where it's important to remember what ds represents. ds is the change in the entropy of the system. If there's no change in the entropy of the system, then in order for the process to take place spontaneously, then there has to be an increase in the entropy of the surroundings, and that can happen only if there's heat transferred from the system to the surroundings. So we can maintain a constant entropy if the system gives up energy in the form of heat to the surroundings. And that would, in order for that to happen, the system must give up some of its energy in the form of heat to the surroundings. And that will lead to an increase in the entropy of the surroundings, which when we have a constant entropy in the system plus an increase in the entropy of the surroundings, the overall change in entropy is greater than 0. So that's what this relationship ends up telling us. Same thing for if we consider we have ds equal to dq reversible over t Clausius inequality. What about for constant pressure? We can rearrange this so that T ds is equal to dq reversible. At constant pressure, we can relate q sub p equal to dh. And so when we substitute dh for dq sub p. So when we do that, we get T ds is equal to dh. Oh, this is a Clausius inequality. Sorry, this is greater than or equal to greater than or equal to greater than or equal to. So the same idea that we use to explain the two conditions for spontaneity from when we hold the volume constant. We hold the pressure constant if we restrict the process to take place at constant entropy, then delta S surroundings must increase. delta S of the surroundings must increase, that means that if entropy is equal to 0, then dH must be less than or equal to 0. So if ds is equal to 0, that means dH is less than or equal to 0. That means in order for a spontaneous process to take place, that the enthalpy of the system has to decrease, and by doing so, it's releasing energy in the form of heat to the surroundings, which causes an increase in the entropy of the surroundings. Alternatively, if the process takes place at constant enthalpy, then there must be an increase in the entropy of the system in order for the process to take place, and that's, as your book suggests, that's basically a restatement of the second law of thermodynamics. So, okay. So the other thing that we did in 3A is we calculated different ways. We learned how to calculate entropy changes for different processes. And we've already talked about if we have an isothermal expansion, we've already seen that in our first and third steps of the Carnot cycle. So that means that our delta S for isothermal reversible expansion, it doesn't matter if it's reversible or not, isothermal expansion, because in our definition of entropy, we're going to use the heat transferred for a reversible process. So it's equal to nRT, natural logarithm V final over V initial. Let's see. We have heat transfers, so we can think of constant volume heating or constant pressure heating. So if we have constant pressure heating, let's say, we have delta S is equal to dQ sub P over T. Well, that's the integral. This is the measurable change in entropy. It's defined in terms of the integral of dQ sub P over T. But dQ sub P, we can substitute with dH, which from the heat capacity, definition of Cp is equal to the partial derivative of H with respect to temperature constant pressure. We can also write this as dH sub P over dt sub P. So dH sub P is equal to Cp dt. So we're going to take this result. I have dQ sub P is equal to dH, but dH is also, I can show, equal to Cp dt. So back in my definition for constant pressure heating, I can substitute dQ sub P with the integral of Cp dt over T for the change in entropy. So if my heat capacity is a constant over the temperature range, I have T initial to T final, then I can take it outside the integral. So I have Cp integral dt over T initial to T final, and that is equal to Cp natural logarithm T final over T initial. So we have two, very different forms for how we calculate the change in entropy, depending on if we're talking about an isothermal expansion or a process where we're heating the system. So you want to make sure you keep those different ways of calculating changes in entropy separate.
In the equation for isothermal expansion, then T is canceled out, correct?
Yes. Yeah. Thank you. Yeah. That's right. That's Q reversible over T. Let's see. And then the other thing we talked about is calculating entropies for phase transitions. phase transition is equal to the heat transfer for the phase transition divided by T. But for a phase transition, we can use the enthalpy of the transition. So we define this in terms of the enthalpy of the transition over T. And that, in part, we can do that because at the transition, for the phase transition taking place, at equilibrium for that phase transition, we have, well, due to the fact that it is at equilibrium, the phase transition can be considered taking place reversibly because it's at a phase transition at equilibrium. You have two phases in equilibrium with each other, undergoing the phase transition. So we have those three different things that you need to remember how to calculate changes in entropy. Okay. Any other questions about that? Yep. Did I make it's okay?
What's the subscript after the delta, like the delta T?
This one? Transition, enthalpy of the transition. Yeah.
So that could be like vaporization or fusion.
Yes. Yeah. Whatever the enthalpy of the transition is that you would be given. And that actually comes up for the next section, which is when we talk about how we calculate. Oh, the other thing I wanted to do, well, even over here, is we can define this in terms of, let's say that we know S at T initial, and we want to calculate S at T final. So we break delta S into S final minus S initial is equal to CP natural log T final over T initial. So then we can solve for entropy at the final temperature. S final is equal to S initial plus CP natural log T final over T initial. So we can use that to calculate. If we're given the value of the entropy at some starting temperature or the initial temperature, we can calculate its value at the final temperature. So we just snuck this in here at the end, but we're going to use it for the next section. So in section 3b, we introduced the third law of thermodynamics. And the third law, well, first of all, what is our definition of the third law? And so we can think of it in terms of a verbal definition and a mathematical definition again. The verbal definition states that the entropy of perfect crystalline, pure and perfect crystalline pure is equal to 0 at T equal to 0. And mathematically, it's essentially equal to the mathematical we can think of in terms of the Nernst heat theorem, which says that the change in entropy approaches 0 assume a value of 0, assuming the substance is pure in a pure crystalline state. And so that leads to the idea of third law entropies, which are entropies calculated for a substance assuming S equal to 0 at T equal to 0. So that's what we mean when we refer to a third law entropy. And so that does two things for us. We can say, okay, if we want S at some T final, we can basically add up all the delta S's starting from T equal to 0 all the way up to T final. And that, in order to calculate that third law entropy, we assume that S is equal to 0, T equal to 0. And so if we can use our calorimetric approach then to calculate our entropy at some final temperature as a function of temperature, starting at an entropy of 0 at T equal to 0. And then we have different contributions. At temperatures very close to 0, we use the Debye approximation, which says that our heat capacity is equal to A T cubed. And then so we can estimate our change in entropy at temperatures very close to 0 by using this in our heat capacity, for our heat capacity. And then where we have a measured value of the heat capacity, we can add up the contribution between whatever this temperature is and our next temperature. Now if our final temperature is somewhere out here where we have to go through some phase transitions, we may have to include a change in entropy which is equal to let's say the enthalpy of fusion divided by T. So that's where we introduced how we calculate the change in entropy for phase transition. Once we get through that phase transition, then we can increase again, let's say until we reach another phase transition where we calculate the change in entropy as being equal to the enthalpy of vaporization divided by T. And then we can continue to heat the system up to whatever our T final is using the integration of Cp dt between those points. So this is how we get at calculating our third law entropy for a substance at some final temperature. We assume that it has an entropy of 0 at T equal to 0. We can use the Debye approximation to estimate the change in entropy to a temperature where we can now measure the heat capacity, and then we can integrate Cp dt up to the transition temperatures, and then add up the contributions to the change in entropy as we go through our transitions up to our next transition temperature, add up the contribution for the phase transition up to the final temperature. So that's how we can get at calculating the third law entropies. And then this leads to the concept of residual entropy. So residual entropy is the term we use to describe when the entropy at T equal to 0 is not equal to 0. Of course, we can't measure that because we can't achieve absolute we can detect it by using a combination of statistical mechanics and spectroscopy. So if we calculate the entropy at some temperature using our methods of statistical mechanics and spectroscopy, and if we see a value that's different from our third law, then that implies that there's residual entropy, which we can interpret using our statistical definition. S is equal to Boltzmann constant times the natural logarithm of the number of microstates available to that system. And so when these methods indicate that there is residual entropy, then we can use our chemical knowledge about the substance to try to interpret how the molecules might orient in multiple microstates within a crystalline lattice to explain the magnitude of the residual entropy that we measure. Let's see. Okay, just the last thing. Everybody good with that? Yeah. The last thing is how we calculate our standard reaction entropies. So if we use this to calculate our standard molar entropy of a substance at some given temperature, I don't know, let's say it's at 298 K. Let's say. If we have the values of our standard molar entropies at a given temperature, then knowledge of these standard molar entropies allows us, so we can use the values of the standard molar entropies, our third law entropies, to calculate the standard reaction entropy. In other words, the change in the entropy of the system for a chemical reaction, let's say, by using our equation that the standard reaction entropy will be equal to our sum over our I products times the stoichiometric coefficients in our balanced chemical equation times the standard molar entropies of our products minus the sum over I reactants times the stoichiometric coefficients times the standard molar entropies for our reactants. And so we can see how we kind of come full circle within our introduction of the third law. Third law stating that the entropy, molar entropy is equal to 0 at T equal to 0, leads to our calculation of third law entropies, which we can do by using our knowledge of the heat capacities and the enthalpies of the transitions. We can use that to calculate standard molar entropies, which we can then use to calculate the standard reaction entropy. In other words, the change in entropy associated with a particular chemical reaction using this equation. So that's the end of chapter 3B. So, any other questions? Should all sound familiar because it's a review of what we've already covered in class. Okay, we'll see you in class tomorrow.